Hello, welcome to lecture number 21. From this lecture onwards, we are moving to a different chapter, and this is a chapter on waves. First, we'll start with barotropic waves, that is, waves where we are not concerned with the effect of variation of density with depth, which we know that if density changes not only with pressure but other constituents, for example, temperature and salinity, we give rise to baroclinic situation. But we'll first start with barotropic waves. And this is the condition, this is the situation where the ocean stratification is not important. And we will see various kinds of waves that can be supported here. And we will discuss the dispersion relation of the waves. So for someone who has not done a chapter a topic on waves, dispersion relation is something, a relationship between the frequency and the wave number of the waves, and we'll see how at different limits we derive different dispersion relations. And we will see the effect of rotation in these waves. And once we have a basic understanding of barotropic waves, we'll move on to understanding internal waves, which are internal to the ocean. So let's start with barotropic waves first. So in this situation, in these barotropic waves, the ocean's stratification is not important. It's not that it's not important, but it's not considered here. So rather the correct statement would be the ocean stratification is not considered here. Rotation is included, but the system is assumed inviscid. And as we have discussed multiple times, inviscid assumption is valid when it's a high Reynolds number flow, and also it is away from boundaries. So let's say we are looking at something within the interior of the ocean, and away from boundaries, surfaces, and also we are assuming that the ocean is homogeneous, or at least the water column in which we are considering the system, in which we'll understand these waves is where stratification is not important. So this is a homogeneous system, so it's a homogeneous inviscid flow. So to gain an understanding of how the system behaves, we will derive something called the shallow water equations. So we'll get to how this um, uh, how this looks like and how we can derive it. And we will, given the fact that we want to understand, we want to get a closed form solution for the dispersion relations, we will have to linearize the system of equations. So we derive the shallow water equations, we develop the shallow water equations, and then we will linearize them. So we've not done this. This is only the things that we are going to do. I'm just mentioning it. We will develop the shallow water equations next, and then we'll linearize them, and then we'll see how we'll solve those equations and we'll derive the dispersion relation. So let's move ahead. So we start with the primitive equations. So as I mentioned previously, these are the cornerstone of geophysical fluid dynamics, and we have derived the primitive equations, and hence we'll only be stating them here. So the primitive equations in the x momentum equation is given by So this is the x momentum equation. Now you'll see that we'll throw away um, the viscous terms, but I'm just writing down the primitive equations just for the sake of uh, revision. So this is v plus fu the z momentum equation, and of course the continuity equation that must be written along with all the above momentum equations. Now, given the fact that we have homogeneous and inviscid, so this goes to 0, this goes to 0, and this is 0 because it is homogeneous. This is inviscid. Okay. So if the horizontal flow field is initially independent of depth, it will remain so at all times. So u and v remain independent at all times. The above equation then reduces to the equations reduce to and then the continuity equation, which is the divergence of the velocity field is 0. So remember that geostrophy is not implied here. So all the acceleration terms survive. That means rotation is the acceleration, the rotation, the Coriolis term is also equal to or has the same order of magnitude as the other acceleration terms in the equation. So remember that the w velocity, I mean here we have the w velocity in the continuity equation. This is the term. Remember that this can have a vertical variation, but u and v are uh, u and v do not depend on z. So if they initially start not being dependent on z, they remain independent of z. So let's draw the schematic of the problem that we are trying to address. I mean, that we are trying to understand waves in. So this is a system. I mean, this is the surface, and let's say this is the bottom of the ocean. So this is a function, I mean the height of the bottom boundary is, let's say, is b, and z equal to 0 is the bottom of the ocean. This is the coordinate system that we have chosen, and h is the mean height from z equal to 0 level, and the surface displacement, I mean displacement of this free surface. So this is the blue line, the blue curve is the free surface. This displacement is represented by this variable eta, and the total height is given by x, y, and as the variable small h, which is a function of x, y, and time. So this is the system that we are studying. This is a 2D system as of now. We have defined all the variables. So now integrate the continuity equation. Integrate the continuity equation over the entire fluid depth. The reason we can do this is in the assumption that we have started with, that it's a homogeneous fluid. Okay, so that is the reason why we can integrate the system. And integrating this one, we have del u del x plus del v del y okay. So this is the this is an integration of the continuity equation, and the boundary conditions here the vertical velocity at the bottom topography is the total derivative of that coordinate. Now, given the fact that this given the fact that we can write down the total I mean the height of the system as this is the eta, or rather going back to the system. So here, so we have b plus h plus eta b plus capital H sorry, this is h plus eta is equal to b plus h. Eta equal to b plus h minus capital H. Please verify this from the figure that eta can be written as b plus h minus capital H, given the fact that capital H is constant. Hence we can write the first expression in terms of the second expression. So h is so eta equal to b plus h minus h. And the other boundary condition, let's say this is A and this is B. So this is the first boundary condition is at the free surface. Okay, so if I had said something else, there might be a correction. So this is at the free surface, and this is at the bottom boundary. Okay, z plus h is the free surface. Sorry, it's the b plus h. This is b, and this is the small h. So b plus h is the surface at which we have the undulating surface, undulating ocean, and the bottom boundary is at z equal to b. So these are two different boundary conditions, the top and the bottom boundary. And the bottom boundary condition is u del b del x plus v del b del y. Now equation the integrated equation, let's call this as equation 5. Equation 5 becomes del eta del t plus del x hu plus del y hv equal to 0. Let's call this equation 6. So this eliminates the vertical velocity. So as the fluid is homogeneous, the dynamic pressure is independent of depth. Homogeneous. The dynamic pressure is independent of depth. So in case of uniform surface pressure, P can be written as rho g eta, rho naught g eta, where rho naught is a reference density. So replacing this value of P, we have replacing the value of P in the above equation, the set of equations, the momentum equations, we have del u del t del x plus v del u del y minus fv equal to minus g del eta del x. See that the right hand side has changed to del eta del x, del v del t plus u del v del x plus v del v del y plus fu equal to minus g del eta del y. And the continuity equation has the form so we have arrived at the end of the derivation. These set of equations are the ones that we were after, and these are called the shallow water equations. Why does the name shallow appear? Is because we assume the length scale of the problem to be much bigger than the height of the problem, and this can be justified in a way. For example, if you think of the ocean is thousands of tens of thousands of if you take the circumference, it's a few thousands kilometer large. Of course there are continents in between, and only you can go without hitting a continent for a few thousand kilometers, but let's say you are far away from the equator towards the south, you might find continuous, you will find a continuous ocean a few thousand kilometers. Okay, nevertheless, so it's a few thousand kilometers long, whereas the depth of the ocean is only, on an average, is approximately 4.5 kilometers. So you can imagine the ratio being multiple orders of magnitude. Okay, so hence, for purposes which are much larger in scale, we can assume the ocean to be a homogeneous fluid, and this is where the barotropic waves that we are going to study exist. And this is not a terribly bad assumption, assuming the ocean to be homogeneous for certain purposes. Okay, so if you are looking at certain other processes, that we'll get to later in this chapter, we cannot assume the ocean to be homogeneous. We'll be missing out on a lot of interesting topics, interesting systems like internal waves in the ocean. But for the case of large scale phenomena, we can assume the ocean to be homogeneous, and that is where these simplification, these primitive equations are simplified to, and these are the governing equations for a barotropic system, and these are called the shallow water equations, or the shallow water model is also, sometimes people also call it shallow water model. Now, if the bottom is flat, so if the bottom is flat, eta is just small h minus capital H. So the above set of equations become so in many cases we will be assuming bottom to be flat, and this is where we will see these forms of the equations appearing. This is the shallow water model, but this is the form where there is the bottom is assumed to be flat. So this is, of course, I mean, this is, we've derived the shallow water equations, and this is for us to remember that we assume that this is the system is assumed to be a single layer. The system is assumed to be a single layer, and no vertical variation is is permitted in the system. Of course, this is not the real ocean. Systems, the properties vary with depth, but as I mentioned, for some phenomenon, this is an appropriate model, and this is actually much simpler again to solve than the full nonlinear equations. I mean, of course, this is also a nonlinear equation, but we'll linearize the system, and we'll see how that linear version of the shallow water, or the shallow water equations once linearized, support certain waves, and we'll see the properties of the waves in the next lecture.